So in this video, we're just going to go through a bunch of past exam questions on Year 2 integration. This video isn't necessarily going to be teaching you how all the methods work because I've already done 12 videos on Year 2 integration and all the different techniques that you can use and what they can ask you to do. I'll include a link to the playlist of Year 2 integration. It should be at the top right hand corner now. I'll also include a link in the description as well. If you want to go through any of the questions that I'm doing here, just pause the video, have a go at the question and then play it in order to get the answer. So here's the first question here. Okay, so for this question, we're told that the integral between 1 and e to the power of 2 of x to the power of 3 natural log of x is this a e to the power of 8 plus b, and we need to find what a and b are. Okay, so what we essentially just need to do is integrate this here. Okay, now as I've talked about before with definite integrals, we don't need to worry about these limits at the start. What we first need to do is actually focus on integrating this x to the power of 3 natural log of x. Okay, so how do we go about integrating this? Well, here we have two terms, this x to the power of 3 and this natural log of x, and they're multiplied together. So this is a clue that we're going to use integration by parts. Now I've given you the formula here for integration by parts because it's given to you in the formula booklet, so you'll have access to it in the exam. And the way that we go about doing integration by parts is these two terms here. One of them we call u and we differentiate this, and the other one we call dv over dx and we integrate this. Okay, so which term do we call which? Okay, so this natural log of x, if you remember, this is quite difficult to integrate. It doesn't have a standard integral, so we want to avoid calling this the dv over dx because that means we're going to have to integrate this. What we would rather do is call u the natural log of x, so we differentiate this instead, and therefore we're going to call the x to the power of 3, we'll call this the dv over dx. Okay, so if we start with this u is equal to the natural log of x, if we differentiate this, it will be du over dx is equal to, and if you differentiate this, this is year 2 differentiation, this is equal to 1 over x, and then this dv over dx is equal to x to the power of 3. If you integrate this, it's going to be v is equal to, if you integrate this, this is just year 1 integration, this is equal to 1 over 4 x to the power of 4. Okay, so if we plug this into the integration by parts formula, so firstly it's uv, so u is the natural log of x and v is 1 over 4 x to the power of 4, so uv is going to be the natural log of x multiplied by 1 over 4 x to the power of 4, and then it's minus the integral of v, which is this 1 over 4 x to the power of 4 multiplied by du over dx, which is this 1 over x. So it's 1 over x like this here, and then dx. Okay, so we can do some simplifying here. So first we have this natural log of x multiplied by this 1 over 4 x to the power of 4, so we can write this in a simpler way as 1 over 4 x to the power of 4 natural log of x, and then it's minus, now we have this integral here, so firstly we have this 1 over 4 which we can take out of the integral to make it a bit simpler, so it's minus 1 over 4 and then the integral of this x to the power of 4 multiplied by 1 over x, which will simplify down to x to the power of 3 like this here. Okay, so we can simplify this further, so this 1 over 4 x to the power of 4 natural log of x, we don't need to touch this, and then it's going to be minus 1 over 4, because remember we took this out here, and then it's the integral of x to the power of 3. Again, this is just year 1 integration. When you integrate x to the power of 3, it's equal to 1 over 4 x to the power of 4, and then remember the plus c on the end, and then we can simplify this further because we have this 1 over 4 multiplied by this 1 over 4, which is going to be 1 over 16 like this here, and then x to the power of 4 and then plus c, so this is the integral of this x to the power of 3 natural log of x. Okay, so now what we need to do is sub in these limits of e to the power of 2 and 1 into this function here and then get it into this form here and then find what A and B are. Okay, so that's what I've done here. I've subbed in the upper limit of e to the power of 2, so it's going to be 1 over 4 and then e to the power of 2 to the power of 4, and then the natural log of e to the power of 2 minus 1 over 16 e to the power of 2 to the power of 4, like this here, and then minus, and then I've subbed in 1 into this function as well, like this here. Okay, so we can do some simplifying for this here. So firstly, we have this e to the power of 2 to the power of 4, so we're still going to have this 1 over 4 at the start. Then e to the power of 2 to the power of 4 is e to the power of 8. Okay, this natural log of e to the power of 2, remember your laws of logs. When you have a power inside a log like this here, you can bring it to the front as a coefficient, so we can write this as 2 natural log of e, like this here, and then this is going to be minus 1 over 16, and then again we've got this e to the power of 2 to the power of 4, so this is going to be e to the power of 8, and then this is going to be minus, and then we have this 1 over 4, 1 to the power of 4, natural log of 1. Remember, the natural log of 1 is 0, so this term here is going to cancel out, and then we've got this minus 1 over 16, 1 to the power of 4, which is going to be minus 1 over 16, like this here. Okay, we can do some simplifying here, so we have this 1 over 4 times 2, so this is going to be half, and then this e to the power of 8. The natural log of e is 1, so therefore we can kind of just cancel this out like this here, and then we've got this minus 1 over 16 e to the power of 8, and then we've got this minus 1 over 16, so this is going to be plus 1 over 16, like this here, and we can simplify this again because we have this half e to the power of 8 minus 1 over 16 e to the power of 8, which if you put into your calculator or just figure it out is equal to 7 over 16 e to the power of 8, and then this plus 1 over 16, and this is in this form here where a is equal to 7 over 16 and b is equal to 1 over 16, so this here is the final answer. Okay, so here's another example question where we're told that a is a constant and the integral between 1 and 4 of 3 root x plus a is equal to 2a squared, and we need to use this information to show that there are exactly two possible values for a. Okay, so what we're first going to do is we're going to integrate this here. So let's first focus on integrating this 3 root x plus a. Remember, root x can be written as x to the power of a half, if you remember your indices law, and we're going to write it like this because it's easier to integrate. So if we integrate this here, so this is going to be 3 times, and then if you integrate x to the power of half, this is just year 1 integration, this is going to be equal to 2 over 3 x to the power of 3 over 2, and then this is going to be plus, and then if you integrate a in terms of x, as a is a constant, it's going to be a x, like this here, and then remember the plus c on the end, and then we can simplify this because we have this 3 times this 2 over 3, so this 3 will cancel out with the denominator 3 to leave us with 2x to the power of 3 over 2 plus a x plus c, like this here. Okay, so this is the answer to this integral here. So now we need to sub in the limits of 4 and 1, and this is equal to 2a squared, and then we need to find the values of a. So if we sub in the limits of 4 and 1 like this here, so it's going to be 2, and then instead of x here, it's going to be this 4, so the power of 3 over 2 plus a, and then instead of this x here, it's going to be 4, and then minus, and then we've subbed in 1 here as x, like this here, and all of this is equal to 2a squared. Okay, so we can do some simplifying here. So here we have this 2, and then 4 to the power of 3 over 2 is equal to 8, and then this is going to be plus, and then a times 4, like this here, we can write as 4a, and then it's going to be minus, so 1 to the power of 3 over 2 is still equal to 1, so this here is just going to be 2, and then this is going to be plus a times 1, so this is just equal to a like this here, and this is still equal to this 2a squared like this here. We can do some more simplifying. So 2 times 8 is 16, and then it's plus 4a, and then if we expand this bracket here, it's going to be minus 2 minus a is equal to 2a squared. And then we can do some more simplifying here. So 16 minus 2 is equal to 14, and then 4a minus a is equal to 3a, and this is equal to 2a squared. So we've got it in this format here. Okay, so we've got it into this format here. So if we make it into a quadratic equation by moving this stuff onto this side, so it becomes 2a squared minus 3a minus 14 is equal to 0. And then if we solve this quadratic here in order to find a, there's loads of ways that you can do this. You can use your calculator, you can use the quadratic formula, or you can factorize it. You can just factorize it into a plus 2 2a minus 7 like this here, and that means that a is either equal to minus 2 or 7 over 2. So these are the two possible values of a, and therefore we have shown that there are exactly two possible values for a, which is what the question asks. Okay, so here's another example where we need to show that the integral between 0 and 2 of 2x and then the square root of x plus 2 is equal to this here. Okay, so like we normally do for definite integrals, let's ignore these limits first, and let's first integrate this function here. Now we have this 2 here, so let's take this out of the integral at the start to simplify it. So we're just integrating this function here, this x, and then the square root of x plus 2. Remember that when you have a square root, you can write it to the power of a half like this here using indices laws, and this here is easier to integrate when it's in this format here. So we need to integrate this here. Now there are two ways that you can integrate this. I think both of them are equally valid. You can either use substitution or you can integrate it by parts. I'm going to do it by parts because I think it's slightly easier, but it's perfectly fine to do it using substitution as well with a user substitution, like u squared is equal to x plus 2, and then you can see you can sub this in here under the square root. But I'm going to do it by parts. So here's the formula for integration by parts. Here again, it's given to you in the formula booklet. So with this, one of the terms we're going to have to call u and differentiate this, and then the other one we're going to call dv over dx, and we're going to integrate this. Okay, and as we talked about with integration by parts, if one of the terms is x like this here, we like to call this u and differentiate this, and then we'll call the other term, so in this case the x plus 2 to the power of a half, we will call this dv over dx and integrate this. Okay, so u is equal to x, so if we differentiate this, it's going to be du over dx is equal to, if you differentiate x, it's just equal to 1. dv over dx is equal to this here, so if we integrate this, it's going to be v is equal to, if we integrate this, so remember this power is going to go up by 1, so it's going to be 3 over 2, so we need to divide by this, so it's going to be 2 over 3, and then x plus 2, and that's going to be to the power of 3 over 2 like this here. Okay, so now what we're going to do is use this formula here. So it's uv, so u is x and v is this here, so it's going to be x times 2 over 3 x plus 2 to the power of 3 over 2 like this here, and then it's going to be minus the integral of v du over dx. So du over dx is 1, so if you times something by 1 it will just cancel out like this, so we don't need to worry about this. So it's just the integral of kind of v here, which is this here, so it's going to be the integral of this here, this 2 over 3, we can take this out of the integral and put it at the front like this here to simplify it. So it's going to be the integral of this x plus 2 to the power of 3 over 2 like this here. Remember that we took this 2 out of the integral at the start, so this entire thing here, we need to times it by 2 because we took this out at the start. Okay, so we can do some simplifying here. Okay, so firstly we have this x multiplied by this 2 over 3 x plus 2 to the power of 3 over 2. So we can write this as 2 over 3 x plus 2 to the power of 3 over 2 like this here. And then it's minus 2 over 3. Then the integral of this x plus 2 to the power of 3 over 2. So this 3 over 2 power is going to go up by 1. So it's now going to be to the power of 5 over 2. Remember, we need to divide by this as well. So it's going to be 2 over 5, and then this x plus 2 to the power of 5 over 2, like this here. Remember, we need to multiply this entire thing here by the 2 at the front, and then we can put a plus c here, like this here, and then we can simplify this. So 2 times 2 over 3 is equal to 4 over 3, like this here, and then 2 times 2 over 3 times 2 over 5 is equal to 8 over 15, like this here. Remember, we have a minus like this as well. So this here is the integral of this. Okay, so now we need to sub in the limits of 2 and 0 into this function here and show it can be written in this format here. Okay, so I've subbed in the limits here. So I've firstly subbed in 2 for all of the x terms, and then minus, and then I've subbed in all of the x terms for 0, like this here. Okay, so we can do some simplifying here. Okay, so firstly, if we start with this term here, so we have 4 over 3 times 2, which is equal to 8 over 3, like this here. And then we have 2 plus 2, which is 4, so this is going to be 4 to the power of 3 over 2. And then it's minus 8 over 15, and then 2 plus 2 again is 4, so this is going to be 4 to the power of 5 over 2, like this here. And then it's minus, so for this term here, we're now multiplying by 0, so this whole term here will cancel out. And then here we have got minus 8 over 15. Now remember, we're minusing here as well, so these two minuses will cancel out and leave us with plus 8 over 15. 0 plus 2 is 2, so this is going to be 2 to the power of 5 over 2, like this here. Okay, we can do some more simplifying. So we have 8 over 3. 4 to the power of 3 over 2 is equal to 8, and then it's minus 8 over 15. 4 to the power of 5 over 2 is equal to 32, and then plus 8 over 15, and then 2 to the power of 5 over 2 is equal to 4 root 2, like this here. Okay, we can do some more simplifying. So this 8 over 3 multiplied by 8 minus 8 over 15 multiplied by 32, if you put this into your calculator, it's equal to 64 over 15. Okay, and then we've got plus this 8 over 15 times 4 root 2. 8 times 4 is 32, so this is going to be 32 over 15 root 2, like this here. Now if we look at our final answer, we want this 32 over 15 factorized out. So let's factorize out 32 over 15 from these two terms here. So it's going to be 32, it's going to be 32 over 15. If you factorize out 32 over 15 from this 64 over 15 here, it's going to leave us with 2, like this here, plus, and then if you factorize 32 over 15 out of this 32 over 15 root 2, we're just going to be left with root 2. So therefore we've got this here, which is the final answer, so therefore we've solved the question. Okay, so here's another exam question where we're told that a curve C has equation y is equal to f of x, and we're told that f dash of x is equal to 6x squared plus ax minus 23, where a is a constant. We're told the y-intercept of C is minus 12, and we're told that x plus 4 is a factor of f of x. We need to use all this information in order to find f of x. Okay, so how do we do this? Well, the thing that's most useful to us is that they give us an equation for f dash of x. Remember that f dash of x is f of x differentiated. So therefore, in order to get f of x, we just need to integrate this f dash of x. Remember, this is the differentiated form of f of x, so in order to get it back to f of x, we just have to integrate it. Okay, so what we're going to do is we're going to integrate this function here. So f of x is equal to this integrated, so 6x squared integrated is going to be 6 multiplied by it, and then when you integrate x squared, it's equal to 1 over 3 x to the power of 3 plus a multiplied by it, and then when you integrate x is equal to a half x squared minus 23, so this is going to be minus 23x, and then remember the plus c on the end. This is important because in order to get the full equation for f of x, we need to find the identity of this plus c. Okay, so we can do some simplifying here, because 6 times 1 over 3 is equal to 2, so this is 2x cubed, and then this here is going to be half a x squared, then this minus 23x plus c. Okay, so we've used this part here. Okay, so now let's move on to this part here where we're told that the y-intercept of the curve c is minus 12, and using this information we can see that c, this constant of integration at the end, is going to be equal to minus 12. The reason for this is if the y-intercept of c is minus 12, what this is actually saying is a point on the curve c, as it's the y-intercept. Remember, when the y-intercept x is equal to 0, so this point here is going to be 0 minus 12. Okay, so what we can do with this is we can sub this, as x is equal to 0, we can sub this into f of x. We can do f of 0 where x is equal to 0, so that's what I've done down here. And then if you do this, this term here will cancel out, this term here will cancel out, and this term here will cancel out. You just leave us with c here, and we're told that when you sub in x is equal to 0, it's equal to minus 12, so therefore c is equal to minus 12. Okay, so we found c, this is minus 12, so now we need to find what a is, okay, in order to get a full equation for f of x, and that's where we're going to use this bullet point here, that x plus 4 is a factor of f of x. Now this here, we talked about this back in year 1 of chapter 7 about the factor theorem, and the fact that if x plus 4 is a factor of f of x, what this means is that f of minus 4 is equal to 0. So what that means is if you sub in x is equal to minus 4 into f of x here, like this here, you get out 0, and therefore what we can do is we can use this in order to find out what a is. Okay, so in order to do this, so x is equal to minus 4, if we sub this into this equation like this here, so for all of the x values we've subbed in minus 4, this is going to be equal to 0. Again, go back to the factor theorem video that we made back in year 1 of chapter 7 where we talk about why this is and how it works. So therefore what we can do now is rearrange in order to find what a is. Okay, so this 2 times minus 4 to the power of 3, this is equal to, if you put it into your calculator, it's equal to minus 128. So we've got this minus 4 squared here, which is 16 times this by the half, so it's going to be plus 8a, and then minus 23 times minus 4 is going to be plus 92. Then it's minus 12 is equal to 0. We can do some simplifying here, so this 8a, we don't need to touch this, and then minus 128 plus 92 minus 12 is equal to minus 48. If you put it into a calculator, and all of this is still equal to 0, move this minus 48 onto the other side, so we get that 8a is equal to 48, and then divide both sides by 8, so we get that a is equal to 6. So this is the identity of a. So therefore what we can do is sub this in here and get out the full equation for f of x. So that's what I've done here. So f of x is equal to 2x to the power of 3. Remember, there is a half here in front of the a. Remember, a is 6, therefore it's going to be 3x squared, like this here, minus 23x minus 12. Okay, so here's another example question where we're told about this graph here, which is figure 3, and this is a sketch of part of the curve with equation y is equal to x minus 2, x minus 4 over 4 root x, okay? And we're told the region R, which is this here, is bound by the curve and the x-axis, and we need to find the exact area of R, and we need to write it in this format here, okay? So as we're finding this region R that is kind of underneath the curve, technically it's above the curve, but it still works the same with integration between the curve and the x-axis here. Therefore, we're going to use integration. We're going to integrate this function here. Now, the limits in this case you can see are between these two roots here. Let's just call these roots for now A and B, okay? So what this question is essentially asking is to integrate between the lower limit, which is this root A, and the upper limit, which is this root B, of this function here for dx. Okay, so what is A and what is B? Now these are of course roots, so remember roots exist where y is equal to 0. So what we can do here is set y equal to 0 and rearrange in order to find x, and these will be the roots and the values of A and B. So therefore this is going to be where x minus 2, x minus 4 over 4 root x is equal to 0. If we multiply both sides by 4 root x, so we get rid of this denominator here, we can do this because we're told that x is bigger than 0, so therefore x cannot be equal to 0, so there's no risk of us multiplying both sides by 0. We get that x minus 2, x minus 4 is equal to 0, so therefore x is equal to 2 and 4. These are the two roots. So here, they're no longer A and B, we can call them 2 and 4. So therefore, what this question is asking us is to integrate between the lower limit of 2 and the upper limit of 4 for this function here. Okay, so let's actually go about integrating this. So firstly, let's ignore the limits to start off with, and let's actually integrate this function here. So the easiest way to do this, in my opinion, so in the numerator we have x minus 2 times x minus 4. So if we expand these brackets here, it's going to be this here, because you've got this x times x, which is x squared. You've got the minus 2 times x, which is minus 2x, and minus 4 times x, which is minus 4x. Add those two together and you get minus 6x, and then minus 2 times minus 4 is plus 8. So that's what happens when you expand this bracket here. And in this fraction here, as we've got 3 terms in the numerator and 1 term in the denominator, we can split up this fraction like this here. So we can do the x squared divided by the 4x to the power of half. We can do the minus 6x divided by this denominator here, and the 8 divided by this denominator here, and therefore we can simplify it like this, and therefore we can simplify it further, because if we say that this is equal to the integral of, so x squared divided by 4x to the power of a half, so this, remember there is a 1 up here, so this is going to be 1 over 4 like this here, x squared divided by x to the power of a half. If you remember how the indices laws work, if you divide two powers like this here, they will minus, so it's going to be 2 minus a half, so it's going to be x to the power of 3 over 2 like this here, and then this is minus 6 divided by 4, which is 3 over 2. Remember this is x to the power of 1, so x to the power of 1 divided by x to the power of a half is going to be 1 minus a half, which is a half like this here, plus 8 divided by 4 is 2, and it's going to be x divided by, so we have this x to the power of a half in the denominator. If we want to take this out of the denominator, remember we need to add a minus in front of this power, so it's going to be minus a half like this here. Okay, so now we have these 3 terms here, which we can go about integrating. This is just year 1 integration. So if we start with the 1 over 4 x to the power of 3 over 2, so this is going to be 1 over 4 multiplied by, and then if we integrate this x to the power of 3 over 2, it's going to be 2 over 5 x to the power of 5 over 2, and then this is minus 3 over 2 multiplied by, and if you integrate this x to the power of a half, this is going to be 2 over 3 x to the power of 3 over 2, and then this is plus 2 times, if you integrate x to the power of minus a half, this power will go up to a half, and then if you divide by a half, it's equal to 2. This is going to be 2x to the power of a half, and then we've got this plus c on the end, and then we can simplify this. So we've got this quarter times 2 over 5. So these two can cancel out and leave us for 2 down here. And 2 times 5 is 1 over 10, like this here. So it's going to be x to the power of 5 over 2, like this here. Minus, and then this will just cancel out to 1. So this is just going to be minus x to the power of 3 over 2. And then 2 times 2 is 4. So this is going to be 4x to the power of a half plus c. Okay, so now we need to sub in the limits of 4 and 2 into this function here. So this is what I've done down here. So I first subbed in 4 for x, for all of the x terms, and then minus, and then I've subbed in 2 for all of the x terms. Okay, so we can simplify this. Okay, so we have this 1 over 10, and then 4 to the power of 5 over 2 is 32, and then minus, and then 4 to the power of 3 over 2 is equal to 8, and then this is plus 4, and then 4 to the power of a half is just the square root of 4, which is 2, and then this is minus, and then 1 over 10, 2 to the power of 5 root 2 is equal to 4 root 2, and then 2 to the power of 3 over 2 is equal to 2 root 2, plus 4, and then 2 to the power of a half, like this, is equal to root 2. So we simplified it to this here. Now this, if you put this all into your calculator, it gives out a value of 16 over 5, and then this is minus this here. If you put all of this into your calculator, you get a value of 12 over 5 root 2. So this is the answer to the integral here. Now, one thing that's interesting, it doesn't, in the mark scheme, you don't actually lose marks for this, which I find quite surprising, because sometimes you can. If you put this here into your calculator, you get out a value of minus 0.194. Now this is negative. The reason that this is negative is because this R region is underneath the x-axis. Remember that if you integrate underneath the x-axis, it gives out a negative value. One thing that could be argued is because it's finding the exact area of R, area has to be positive, so technically this wouldn't actually be the final answer. Technically you would have to multiply this by minus 1, so it would become 12 over 5 root 2 minus 16 over 5. This is a positive number, and therefore this is the area because it's a positive number. However, in the mark scheme it says that it can actually allow this answer as well, even though it's a negative number. But I just thought I'd note it because sometimes some mark schemes might be a bit more specific and they might want to give the area as a positive number. Okay, so here's another past exam question. Okay, so for part A, we need to use the substitution x is equal to u squared plus 1 to show that this integral here between the limits of 5 and 10 can be written as this integral here with the new limits as p and q. So firstly, let's just plug in this substitution here for the x term. So we have two x terms, one here and one here. So if we plug in the x is equal to u squared plus 1, it becomes this here. So for this x here, I've plugged in u squared plus 1, and for this x here, I've plugged in u squared plus 1. And we can do some simplifying here, because this plus 1 and this minus 1 will cancel out, and this plus 1 and this minus 1 will cancel out to leave us with this here. And we can do some further simplifying, because here we have the square root of u squared, which is just equal to u. So we have this very much simplified format compared to this up here of this 3dx over u squared 3 plus 2u. Okay, now there are two more things that we need to do here. The first one is we need to get rid of this dx here for a du. And remember, with substitution, the way that we do this is if we consider this equation, this x is equal to u squared plus 1, we're going to differentiate this in order to get an equation for dx. So if we differentiate this, so on this side it will become dx over du, and this is equal to, and then on this side, if you differentiate u squared, remember differentiating in terms of u here, it will become 2u, and this is just a constant, this plus 1, so this will just go away, and then multiply both sides by du. So we get that dx is equal to 2u du, and now we have an equation in terms of dx, so we can sub out this dx here for this 2u du. So that's what I've done here. We can do some simplifying here because we have a u up here and a u squared down here. So this u will cancel out with one of the u's down here, and this 3 will multiply this 2 to leave us with 6 in the numerator like this here. So it's 6 du over u3 plus 2u, which is what we've got here. The other thing that we need to do is we need to change these limits here. And as we talked about with integration by substitution, the way that we do this is by plugging, remember these limits at the moment are in terms of x is equal to 10 and x is equal to 5. We need them to be in terms of u. And the way that we're going to do this is these x values, we're going to plug them into this equation here and get out the corresponding u values. So if we start with the x is equal to 5, so using this equation here, it will be 5 is equal to u squared plus 1, move the plus 1 onto the other side, so we get that 4 is equal to u squared, and then square root both sides, so we get that 2 is equal to u. So this is the lower limit. We're told p and q are positive constants, so we don't need to worry about the plus or minus square root. And then if we consider the x is equal to 10, so this will be 10 is equal to u squared plus 1, move the plus 1 to the other side, so we get that 9 is equal to u squared, and then square root both sides. So 3 is equal to u. So this is the upper limit. So therefore, this integral is this here, where we have the correct format here, and the lower limit is 2, and the upper limit is 3. And then for part B, we need to show that this integral here can be written as the natural log of a. So essentially we just need to solve this integral and show it can be written as a natural log. And as in part A, we use a substitution to show that this integral can be written in this format here. What this question is essentially asking us is just to show that this integral here can be written as a natural log like this here. We need to find what a is. So we need to integrate this here. Okay, so let's ignore these limits for now. Let's first focus on integrating this 6 over u 3 plus 2u. Now this we cannot directly integrate, however we've talked in this chapter about how to integrate functions like this by splitting it up into partial fractions. So this u 3 plus 2u under 6, we can split this up into two partial fractions, one of them having this denominator of u, and we'll give it the numerator a, plus, and then the other fraction is going to have the denominator 3 plus 2u, and then the numerator b, and a and b are constants that we need to find. Okay, so we need to solve these partial fractions, okay? So to solve partial fractions, the first thing that we need to do is we need to multiply this whole equation here by this denominator. So the u and then the 3 plus 2u, like this here. So if we start with this term here, this u3 plus 2u will just cancel out with the denominator to just leave us with the numerator 6, like this here. And then if we move to this term here, this u will cancel out with this u to leave us with a multiplied by 3 plus 2u. So it's going to be a and then 3 plus 2u, and then we move to this term here, this 3 plus 2u will cancel out the 3 plus 2u denominator and leave us with b multiplied by u, like this here. Now from here there's two ways that you can solve the equations from here. You can either use substitution or you can compare the coefficients. I always use substitution because I think it's a lot easier. So if we start with this bu here, if we let u equal 0, therefore this term here will cancel out and just leave us with 6 is equal to, and if you sub in u is equal to 0 here, this will go away and it just leave us with 3, so this will be 3a, and then divide both sides by 3, so we get that a is equal to 2. And then if we focus on this bracket here, if we make the u here, we let u equal minus 3 over 2, therefore this term here will cancel out because this bracket here will be equal to 0. So we'll just be left with 6 is equal to, and then we sub in u is equal to minus 3 over 2 here, we get minus 3 over 2b, and then divide both sides by minus 3 over 2, so we get that b is equal to minus 4. So therefore here a is equal to 2 and b is equal to minus 4. So therefore we can sub this in to the integral. So it becomes the integral of this 2 over u minus this 4 over 3 plus 2u, and then we can go about integrating this here. So if we integrate this, so let's start with this term here. So it's going to be 2 multiplied by, and then you can think about this like 2 multiplied by 1 over u, this here. This 1 over u, we've talked about this a lot in integration. When you integrate this, it's equal to the natural log of the modulus of u, like this here, and then it's going to be minus 4 multiplied by, so again, think about this like 4 times 3 plus 2u under 1, like this here, so we need to integrate this here. This is the exact same. This is going to be the natural log of 3 plus 2u this time, because we've got this 1 over this here, so it's going to be the natural log of the modulus of this. But the one key thing with this, as we've talked about in this chapter, that we also need to divide by the coefficient of u here, which is 2. Here we didn't need to do this because there isn't a coefficient of u, but here we have a coefficient of 2, so we need to also divide by 2, so it's going to be a half like this here, and then 4 times a half is 2, so it's going to be minus 2, and then the natural log of the modulus of 3 plus 2u, and then remember the plus c on the end. Okay, so we've shown the integral is equal to this here, so now we just need to sub in the limits of 3 and 2. So that's what I've done here. So I've subbed in 3 for u, and then it's minus, and then I've subbed in the 2 for the u, like this here, okay? So we can do some simplifying with this. So this is still going to be 2 natural log of 3, and then minus 2 natural log, and then this here is equal to 9, and then it's minus 2 natural log of 2 minus 2 natural log, and then this here is equal to 7, and then we can do some more simplifying here. So if we focus on kind of these individually, so 2 natural log of 3 minus 2 natural log of 9, if you remember the laws of natural logs, if you minus a natural log from another one, you can divide what's inside the natural logs. So this can become 2 the natural log of 3 divided by 9, which will be 1 over 3, and then this is going to be minus 2 natural log, and then we've got this 2 minus 7, so it'd be 2 divided by 7, so it'd be 2 over 7, like this here. And then we can do some further simplifying. So we have the natural log of 1 over 3 minus the natural log of 2 over 7, so we can write this as 2 natural log of 1 over 3 divided by 2 over 7, which is equivalent as 2 natural log of 1 over 3 multiplied by the flipped fraction, which is 7 over 2, which is equal to 2 natural log of, it's going to be 7 over 6, like this here. Now we need it in this format here, the natural log of a. We can't have this 2 at the front, so what we're going to do, we're going to bring this 2 into the natural log as a power. So it's going to be the natural log of 7 over 6 to the power of 2, which is going to be the natural log of, so 7 squared is 49 and 6 squared is 36. So therefore this here is the final answer, where this a term here is this 49 over 36. Okay, so here's another example question where we're told about this figure here that is a sketch of the curve C with this equation here. So curve C is this curve here, and we're told about the point P with coordinates 4, 15, so this is this point here, and we're told that the line L is the tangent to C at the point P. Okay, so the line L is this straight line here, and it's a tangent at the point P to the curve C, and we're told about the region R that is bound by the curve, the line L here, and the y-axis, and this is R, and we need to show that the area of R is 24. Now, to be honest, I think this is a really difficult question. It doesn't actually use any year 2 content. It's all year 1 integration and stuff like that. However, I think it's a really difficult question. This is reflected in the fact that it's got 10 marks available. There's a lot going on in this question, okay? So I would always advise of a question like this, and when you're given a diagram like this, is to draw on the diagram, because I think it helps you visualize how to solve the problem and how to find the area of R. And to do this question, I think it's best to split up R into two different shapes that are above and below the x-axis, okay? What we're going to say is this bit below the x-axis, we're going to call this shape 1 or S1, and this bit above the x-axis, we're going to call this shape 2 or S2, okay? And let's focus on these individually, okay? So this S1 down here, this is actually quite easy because this is just a triangle, okay? And remember that the area of a triangle is just half times base times height, with this being the base and this being the height. So therefore, if we find the base and the height, we can just find the area of S1. It's to do with this line L here. This is the point where it intercepts the x-axis, and this is the point where it intercepts the y-axis. So we just need to find these points here in order to find S1. Okay, now S2, which is this bigger shape here, is a bit more awkward, okay? So it's underneath the curve C, so on some level it's going to involve integration, okay? Now if we draw on this, now you can see that if we integrate the curve up to P, now remember we're told that P has the coordinates 4, 15, so the x coordinate here is 4. So if we integrate from 0 to 4, so underneath the curve here, we would get this entire area here. Now what's good about this is we do have the area R as part of this, but we also have this big area here that we don't want in our answer. But what's good about this area is a triangle. Here, here, and here, with this being the height and this being the base. Again, if we can find the height and the base, we can find the area of the triangle, and then what we can say is that the area of S2 is equal to the integral that I just showed, the integral of the curve between 0 and 4 minus this triangle. Remember that the area of R is equal to S1 plus S2. So therefore what we can do now is actually go through the steps of actually finding this. We need to find S1, which is this triangle down here, and we need to find S2, which is this integral between 0 and 4. We're going to write this in a different way actually. So S2 is equal to the integral, the lower limit is 0 and the upper limit is 4, of this equation here, this 5x to the power of 3 over 2 minus 9x plus 11 dx minus the area of this triangle here. So the order in which you do things here isn't too important. You could start with finding the integral for S2, or you could start with finding the areas of the two triangles here. I'm going to start with the triangles. Now what's important for the triangles is finding these 2 points here. We need to find this point here to give us the height of the triangle in S1, and we need to find this point here to give us the base of the triangle in S1, and also to give us the base of the triangle in S2 as well, because we know that this here is 4 because we're told that P has an x coordinate of 4. In order to find the base though, we need to know this point here as well. We need to know the x coordinate here as well. Okay, so in order to find these points here, now both of them are to do with the line L. It's the x-intercept here and the y-intercept here. So let's find the equation for the line L in order to do this. Now, L is a straight line. Now, remember back to year 1 of chapter 5, the equation of a straight line is this here. Now, we need a point on the line and we need the gradient of the line. Well, we know a point on the line because we're told it goes through the point P, which is 4, 15. So that's not a problem. We need to find the gradient of the line, and we can do this because we're told that it's a tangent at the point P. So what we can do with the curve, we can find dy over dx, and then find dy over dx when x is equal to 4. This is the gradient at this point on the curve, and this will also be the gradient of the line L because that's a property of tangent. So therefore dy over dx is equal to, so if we differentiate this here, so we've got 5 times, and if we differentiate x to the power of 3 over 2, it's going to be 3 over 2x to the power of a half, and then it's going to be, if we differentiate 9x here, it's just going to be 9 like this here, and we can simplify this because 5 times 3 over 2 is equal to 15 over 2 like this, and then x to the power of half minus 9. Now we're going to sub in x is equal to 4 in order to find the gradient of the curve at this point. So this is going to be 15 over 2 and then 4 to the power of half like this here minus 9. Now 4 to the power of a half is 2 times that by the 15 over 2 here, and this should be 15, and then minus 9 is equal to 6. So this here is the gradient of the curve at this point, and therefore it's going to be the gradient of the tangent as well, which is line L. So we know the gradient up here. So therefore we can sub these properties in order to get the equation of the straight line. So it's going to be y minus y1. Now the y coordinate of P is 15, and this is equal to m, which we figured out is 6, and then it's going to be x minus x1, which is 4, like this here. So this is an equation for the line L, okay? So now what we're going to do is find these 2 points here. So if we start with this one here, so this is where it intercepts the x-axis, so this is where y is equal to 0. So if we sub in y is equal to 0 here, it's going to be minus 15 is equal to 6, and then x minus 4. Divide both sides by 6, we get minus 15 over 6 is equal to x minus 4, and then bring this minus 4 to the other side, so we get that x is equal to 3 over 2. So here x is equal to 3 over 2, and then we find this point here, so this here is the y-intercept, so this is where x is equal to 0. This is going to be y minus 15 is equal to 6, and then x here is equal to 0, so in the bracket now it's going to be minus 4. Y minus 15 is equal to 6 times minus 4, which is minus 24. So therefore y is equal to, remove this minus 15 onto the other side, we get that y is equal to minus 9. So this here, this point, y is equal to minus 9. Okay, so let's figure out the area of these two triangles. Remember, the area of a triangle is half times base times height. So if we start with the area of S1, so this is this triangle here. So the base is this line here, and we figured out that this x coordinate here is 3 over 2. So therefore, so area is half times base, and therefore as this x coordinate here is 3 over 2, the length of the base here is going to be 3 over 2, and this is multiplied by the height, so this is this line here, and as we're told that this y coordinate here is minus 9, this means that the length of the height here is going to be 9. So therefore it's half times 3 over 2 times 9, which if you put this into a calculator is equal to 27 over 4. So this is the area of S1. So now let's consider the area of the triangle in S2. So remember, this triangle is like this here, where this here is the base, this here is the height. Okay, so we know that this here is P, and we're told that the x coordinate of P is 4, so therefore the x coordinate here is going to be 4. We know the x coordinate here is 3 over 2, so therefore the base here is going to be 4 minus 3 over 2, which is equal to 5 over 2, and therefore the height is this here, and we're told that the y coordinate of P is 15, so therefore the height is going to be 15, so therefore the area is going to be half times base, which is 5 over 2, times height, which is 15. If you put this into a calculator, this is 75 over 4. So the area of the S2 triangle is 75 over 4. Okay, so the area of S2 is this integral here minus the triangle. So let's figure out this integral here. So firstly, let's ignore the limits of 4 and 0 and focus on integrating this 5x to the power of 3 over 2 minus 9x plus 11. So this is going to be equal to, so if we integrate this here, it's going to be 5 times, and then if we integrate x to the power of 3 over 2, this power is going to go up to 5 over 2, so therefore it's going to be 2 over 5x to the power of 5 over 2, like this here, minus 9 times, and if you integrate x is equal to half x squared. If you integrate 11, it's equal to 11x, and then remember the plus c on the end, and then we can simplify this. We've got this 5 times this 2 over 5, this will cancel out, just leave us with 2x to the power of 5 over 2, then this minus 9 times a half is equal to minus 9 over 2 x squared, and then plus 11x plus c. So this here is the answer to this integral. So now we need to plug in the limits of 4 and 0, which is what I've done down here. All of these 0 terms will cancel out as we're multiplying by 0, and then these other terms here, if you put these into your calculator, you get out a value of 36. Okay, so this is the answer to this integral here. Now, as we talked about, S2 is equal to this integral, which is 36, minus the area of the triangle that we figured out before is 75 over 4, which if you put this into your calculator is equal to 69 over 4. So this here is the area of S2. So therefore the area of R is equal to the area of S1 plus the area of S2. We figured out that the area of S1 is 27 over 4 and the area of S2 is 69 over 4. If you put this into your calculator, it gives out the value of 24, which is what's required. So as I said, I think this is quite a long and quite complicated question. That's why it's worth all 10 marks. It uses quite a lot of different skills, and I think it's quite difficult kind of realizing how kind of the shapes work with finding the area of R, but that's how you get all 10 marks.